Welcome to the Swayam Prabha series in computer science. As a part of this series, this is a course on artificial intelligence. We are in unit 5 on module 33, which would be the continuation of a last class where we start with embeddings and that we tried with word to vector. And today's it is a continuation of that. We will see another technique called GloVe, where GloVe represent global vectors for word representation, and in continuation of that the contextual embeddings that is very common today, which is in BERT. And just a quick recap of our last class. We had a sliding window over the entire corpus, and if you remember, there was a forward pass from the input to the hidden neuron and then the softmax, and from the softmax we computed the cross entropy loss, and after this it is the back propagation from output from the right towards the left. And through back propagation we had a tiny update of the weight matrix, and in fact the first region of the weight is going to be the embedding that we saw in the last class. So there we looked at one window at a time, it never sees the whole corpus picture. In this session would be the other way around, where we'll be seeing the entire corpus structure in order to get how the words coherently look at each other. So word to vector, it is local, it learns from the center context brass, where one window at a time, and it captures fine semantics, but it ignores the global counts, and it is slow on a big corpora because we are going to be one window by window. In the count based, which is global, there is a co-occurrence matrix, which is what we are going to see it. So this is the other technique where we will use the whole corpus than against the earlier one, and here it is a one shot computation. Instead of building one by one, here it is at one shot we will be capturing the entire co-occurrence, and through that we will be building the embedding. So GloVe, it combines both global as well as the local prediction style. So how it computes, this is again with respect to a paper in 2004 by these authors Pennington and Shahar Manning, and this goes generally by this formula. We have Wi. Wi is the weight of that particular word, and Wj is the context vector. We call this as context, and this is the regular. So we see how that particular word and the context vector how are close to each other, and along with this we will add the bias of that word as well as the context vector of the word, that should be equal to the co-occurrence xi. So xi is whether how many times the word appears close to each other. So xij is the number of times j appears near word I, and wi, wj are two vectors per word. One is called as that particular word vector, and wj is the context vector. Example is, if we say the cat sat, if we take these two words, this can be wi and this can be w context j. So for wi the context is cat, if it is a word, the context word is sat, and for each of it we have the bias, again it is a neural networks term. So let us take a small example, again a very simple example that we have seen in the previous classes. We will take the same example. We will compute the co-occurrence matrix, and from the co-occurrence matrix we will see how an embedding is done using GloVe representation. Suppose let us take S1 corpus, some toy corpus. The cat sat on the mat, and if you see the vocabulary, we have the cat sat on mat, and in S2 the same words are there, the sat on the mat, same words, except these two are going to be different. So it is a 6 cross 6 matrix. How this would be, in the row is 6 and the column there are 6 matrix. So xij is going to be +1 every time j sits near i's window, that we will work out in a minute. For example, cat in S1, the cat sat, Again, neighbors for cat are going to be the as well as sat. For dog, it is going to be the as well as sat. And using that, we will see how the co-occurrence matrix is created. So, for each co-occurrence, we will add a +1 to it. So, this is an example of co-occurrence matrix. Let us say this again, the example is the cat sat on mat and the dog sat on mat. So, if we say, if we take the first statement, the cat, so the next word is cat, the context word is for the context word is cat. So, wherever the appears, the context where we are going to give the x value as x, the cat, we are going to give the value as 1, and then the other things are going to be 0. Similarly, cat, the also we are going to have 1. Then sat, the, again it is 1, on, the cat sat on the mat. So, it would be on the and the on, both are going to be 1. And how many times on appears near cat in the whole of corpus? It is 2 times. Similarly, this 2 represents the number of times mat appears near the either towards the left or towards the right. So, it is 2 times. So, if you look at those 2 statements, this is the entire co-occurrence matrix, which is X. Now, if you look at this table, the whole diagonal region, it is going to be 0. Why? Because there is no way the 2 words appear close to each other. We cannot say the, cat, cat, sat, sat, nowhere it appears in the corpus. So, this diagonal is going to be 0. So, and again it is going to be symmetric in the sense where there is cat and sat, sat, cat will be 1. With respect to cat, sat is 1, and with respect to sat, cat is 1. So, it is going to be the entire matrix is going to be symmetric. So, these are the properties of it. Now, what is the use of this matrix? We will calculate J. J is an error of to create the embeddings. So, what is the error that we get using this co-reference is sigma f xij. Xj is going to be the weight vector that we will do it in a minute, with wi with wj. Wi is going to be this portion, which is this vector. So, each, say for the, if suppose wi is going to be the vector is 0 1 0 2 2 1. So, that represents this wi, and for the context vector is wj, which is going to be cat. If it is cat, it is going to be 1 0 1 0 0 0. So, wi wj, it is the dot product of that particular word vector multiplied by the context vector of that particular word plus the bias for both vectors minus logarithm of how many times the occurrence has occurred with respect to xij. This is got from this, exactly is got from that the numbers, and that we are summing over the entire metric structure, and this we are actually squaring it. Why we are squaring is to, sometimes we will have the positive as well as the negative. So, in order to have only the error, we just get the squared error. So, if we take wi wj plus bi bj minus xij, it is the squared error, it is predicted log count versus actual log count, and f xij, it is a weighing function, and this is very important because it will rule out how many the frequent terms like the, which appears with cat, the dog, the mat, all that can be discarded through this function. And similarly, if we have number of zeros, if you take this matrix, it is sparse, there are number of zeros, so that can also be discounted. So, we will take only the main signal, that is the essence of this fxij function, and that we will show it in a minute. So, this actually runs across the entire matrix, so it is sum. this is the f of x that we are talking about. This portion is what we are looking at now. This is given by x max with the exponential of alpha, where typically the alpha is going to be 0.75 and x max is 100 in that sense, number of maximum time it occurs. I say some estimated value, we will take it as 100. So if x is less than x max, we will take this value x by x max exponential alpha, otherwise f of x is equal to 1. So why do we do that? Because if rare pair, if it is x is equal to 1, if there is only one pair that is appears, the mat one time only it appears and doesn't overfit, we will just give a very small value so that it does not affect the weight. And very frequent, suppose the mat, for example, the is an example that appears all the time, and that again it is capped to 1, it does not matter. Whereas something which is medium, 30 times it appears. So it is approximately 0.4 is the weight, and this is the main signal. So this will get captured through this formula. So given for f of x, when we calculate according to this, multiplied with the vector wi and wj, and we get this wi and wj through this vector. So suppose we take the cat, the wi is this vector, cat is this vector wj, along with the bias of the same minus how many times the occurrence has occurred with respect to each of the words, and that we are squaring it. So this is the objective function of GloVe. So using that, we will do a small problem here. Suppose we say w cat, and here we are having again the same method we are using, where at start the embedding the vectors are going to be random in nature. Assume that w cat has a context vector of, say, has the vector of 0.5, 0.1 and 0.4 with the context vector of 0.3, minus 0.1 and 0.4 with b as 0.05 and b the bias of sat is 0.02, these two vectors. This is the embedding vector, and x cat sat is going to be 1. This we got it from the co-occurrence matrix, which is from the slide 6, the earlier slide that we had. And because log of 1 is 0 at this slide, so this value of the objective function log x cat sat is going to be equal to 0. So now we will compute the residual function w cat multiplied by w, how many times cat and sat occurrence with each other. This is actually 1, so logarithm is 0. Now in order to compute this structure wi with respect to wj, we are taking 0.5 multiplied by 0.3 plus 0.1 multiplied by minus 0.1 and minus 0.4 multiplied by 0.4, and that we would get as 0.02. Now the residual r is going to be minus 0.02 plus 0.05 plus 0.02 minus 0, which is here. So it is going to be 0.05, r is 0.05. This we have seen, yeah. Now with x cat and sat as 1, and suppose we take x max as 100 and alpha as 0.75, then we will have f value as 1 by 100, which is this function here. We are using this function 1 by 100 to the exponential 0.75, we will get approximately 0.032, and when we will multiply the gradient dou j by the weight of it, dou w cat, we get 2 times f of xij plus the residual value what we got as r, which we got from the previous slide here 0.05, multiplied by the vector of w sat. So we will get the value as 0.00096, and all these there is only a slight change. And suppose we update that with a learning weight of 0.05, we get these values 0.4995, 0.10002 and minus 0.4. If you see, these are very slight change in weight, but if we repeat a million times a number of over the number of iterations, this might improve. So at the end of training, we would get the values to be like this, the embedding w cat to be like this. Earlier we had the w cat value to be 0.5, 0.10 and minus 0.4. 0.5, if we see that 0.1 and minus 0.4. After one small iteration, we get this reduced to this. Now, after a number of times, this will again improve and such that our objective function is realized. So, this should be actually, this is the loss that should be minimized. So, our objective is to see that this gets satisfied. Wi, Wj, Bi plus Bj should be equal to the number of times the occurrence should be the same and the logarithm of the number of occurrences. So, this Wi and Wj, these are the context vectors, the embedding, the starting embedding values that we have designed, and this will get changed after a number of iterations. So, this is with respect to GloVe. So, at the end of training, we get Wi and the context vector also W dash I. So, final GloVe embedding would be Wi plus W dash I. So, why we are summing up, both vectors carry the signal, and averaging acts as a tiny ensemble like we have seen in our small toy problem. So, often gives a small but a consistent boost over the entire stream. So, if we look at the differences between word to vector and GloVe. So, in the last class we have seen word to vector, where we had the information use is only local windows, and only at that particular point we have looked at only one word, and based on it the vector is changed. Whereas in GloVe we took account of the entire corpus. The training signal here is going to be predict the context word, whereas here it is the log of occurrence of the count. The loss is with here with respect to cross entropy. In GloVe it is going to be weighted squared error, and memory it streams the entire corpus, and in this case it is sparse because number of occurrences as we see in the example they were zeros, it is actually sparse. The training speed here it is very slower because we are looking at only one particular word at a time. Here it is faster because at one matrix the entire corpus is built as an occurrence matrix. The embedding output it is only one W. So, if you remember it is only one row of matrix has the word embedding. Here we get two embeddings, W as well as the context one. Again the strength is going to be the whole corpus statistic, it is fast, it captures global regularities, and there are actually pre-trained vectors shipped by transport in various cases like 6 billion parameters, 42 billion and 840 billion tokens. It is available in the net that we can use it straight away. But the limitation here is there is only one word vector per word. For example, if we say a bank, whether it is a river bank or a money bank, the same vector representation holds good. By that we cannot say which bank it is. So, there is no word order like, because we saw it is symmetric, the matrix is symmetric, cat sat and sat cat are going to be the same. So, out of vocabulary words they have no vector towards it, and we need an vocabulary fixed well in advance. So, these are some of the limitations. So, the biggest limitation is the polysemy. Polysemy is this where we have same word and different words, and that is where our bird comes into the picture. So, this is the same thing that I described. If you take the two sentences, I sat on the river bank and watched the water. I deposited the check at the bank before noon. In this case, both bank will have the same vector representation. So, again this is the biggest disadvantage, and this is a river bank and money bank receive the same vector, and in order to avoid that, so what we can do next in order to solve this issue is the contextual embeddings that would be given by BERT. So, suppose for example the vector bank it is 0.12 minus 0.31 0.04, it is the same vector every time, it is trained 1. When we are coming to BERT, which is our this topic, the next topic, here bank S1, there will be two different vectors for it. The river bank as one vector and money bank as another vector, and that is given by a term called self attention. So, in this session we will be doing a small example of what self attention is it and how it is calculated, and this is typically done in a BERT technique. So, in another few sessions we will be only dealing with BERT. First we will look at how BERT as computation is done, then we will look into the theoretical underground of framework of transformer, and then the practical implementation of BERT. So, the self attention, the big idea is this. So, every word in the sentence, it looks at the other word and asks, how much should I pay attention to you when building my own new vector? Say for example, let us take the same thing, the cat sat. When the word cat builds it new contextual vector. So, this cat alone, if it wants to build a new vector, again let us assume there is only 4 dimension, it not only decides its own value, but it will also decide the reference point to what is the meaning behind the, what is the meaning behind cat, not actually the meaning, but we call that as attention. So, it might decide, this is an example, say pay 0.1 attention to the. So, suppose this is a slight example, this is a toy example, this 0.1, 0.5, 0.4 is just at random, just to include how to represent it. Suppose it says cat is pay 0.1 attention to the, 0.5 attention to its own self which is cat, and 0.4 attention to sat. Then the new vector of cat, we can write it as 0.1 into vector of the plus 0.5 into vector of cat plus 0.4 into vector of sat. So, how does, now we will see how does this attention coming from, where do we get this attention? It is by means of 3 factors. One is called is query, what am I looking for, key is what do I offer, and V is what info do I carry, and the QI is going to be having a representation of Xi, which is the input value multiplied by WQ. WQ is the weight matrix given by the neural network. And if you see WQ, WK and WV, all the 3 are going to be of the same dimension type. So, these are 3 weight matrix from the neural networks. To start with, all the weights are going to be random, and after a few iterations these weights will get adjusted. So, these weights WQ, K and V, these are the parameters the neural network learns by gradient descent, and Xi is with respect to the input that we give. Suppose for example, X can be cat. So, cat multiplied by WQ, cat vector multiplied by K value and cat multiplied by V value. So, now the attention, given these, the attention is calculated as softmax of Q multiplied by K transpose divided by root of dk, dk is the dimension, multiplied by V, V is the value, where Q query, K is key term and root dk is the maximum value, and why we need it is to saturate it so that the value does not grow big, and that multiplied by V, where QKT is every query meets every key, and these are the raw scores, divided by root dk so that it does not saturate, we have the finite number space. Softmax, again we have seen it converts the value into a probability so that the entire probability of the output goes towards 1. This weight multiplied by this value V, weighted blend of the vector, the value vector that is given as a result of attention. Now, we will do the example of calculating the attention using the same example, the cat sat. So, we have 3 tokens, the cat sat, and we will take the dimension to be 4. Actually, the dimension here in practical BERT it would be 768, but for our reference it would be 4. and QKV dimension, let's take DK to be 2. So, if you take the input embeddings token x0, x1, x2 and x3, the dimensions, let's take this to be the, we have 4 values here, the dimension space is 4, cat as 4 and sat as 4. So, till now in this session we have seen two topics, one is GloVe, another one is the BERT technique that we have just specified only the introduction to it, and in the next session we will be taking it forward. This example we will calculate the entire self attention mechanism on this representation and see how cat is related to the and how cat is related to sat, and after that we will do an implementation of it using Python. In this session we have seen two topics, which would be GloVe and BERT technique, and in BERT we have identified the self attention mechanism, which deals with query, key and value of that particular word, and we have also looked at the small example with which we can work out the attention. In the next class we will continue with this example, find out the attention of this core, and we will also do an implementation to it. Thank you.